What if a signal travelling through the emptinesses between stars did not fade, but grew stronger? Somewhere beyond the distant orbit of Neptune, far past the last influence of sunlight, a faint whisper of energy is moving through space. It is not a burst, not an explosion, not a sudden flare. It is steady, persistent. And according to the instruments that have detected it, it is becoming more intense over time. That alone should not be possible, because everything we understand about the universe tells us the opposite should happen. Signals weaken as they travel. Light spreads out, energy disperses. Whether it is a radio wave from Earth, a pulse of light from a distant star, or a beam of radiation crossing the void, the rule is always the same. The farther it goes, the weaker it becomes. This is not a theory. It is one of the most fundamental principles in physics, described by what scientists call the inverse square law. As distance doubles, intensity drops to a quarter. As distance grows vast, signals fade into near nothing. And yet something out there is not following that rule. According to data collected over years, a signal originating from beyond the protective bubble of our solar system appears to be strengthening as it moves through interstellar space. Not dramatically, not explosively, but measurably, consistently, enough to make scientists pause, enough to make them question whether the emptiness between stars is truly empty at all. To understand why this is so unsettling, you have to imagine the scale involved. You are no longer within the comfortable boundaries of Earth. You're not even within the orbit of the outer planets. You're drifting far beyond Pluto, past the Kuiper belt, into a region where the sun is no longer dominant. Here sunlight is faint. Temperatures are unimaginably low. The solar wind, once a powerful stream of charged particles flowing outward from the sun, begins to slow and weaken. Eventually you reach a boundary, not a sharp edge, but a transition. This is the heliopause, the distant region where the influence of our sun gives way to the broader environment of the galaxy. Beyond this point lies interstellar space, a place shaped not by our star, but by the combined forces of countless others, along with magnetic fields, cosmic radiation and structures we are only beginning to understand. It's here in this vast and quiet region that something strange has been unfolding. A signal, faint at first, almost indistinguishable from background noise. But over time, as measurements accumulate, a pattern begins to emerge. The intensity is not decreasing as expected. Instead, it fluctuates, and in some regions it appears to rise. You might wonder if this is simply an error, a malfunctioning instrument, a misinterpretation of data. After all, space is a difficult place to measure. Signals are weak, distances are enormous, and the slightest calibration issue can create illusions. Scientists considered all of that. They checked the instruments, reanalyzed the data, compared readings across different sensors and time periods, cross-referenced findings with models of the interstellar medium, and still the anomaly remained. According to NASA, instruments aboard Voyager 1 have continued to provide data from beyond the heliopause, offering humanity its first direct measurements of interstellar space. These readings include cosmic ray intensity, magnetic field strength, and plasma wave activity. Over time, scientists noticed variations that did not align neatly with existing models. At first, the changes were subtle. Small increases in detected energy levels, slight shifts in particle density, nothing that immediately demanded a rewrite of physics. But as the data accumulated, the pattern became harder to ignore. Something in this region of space is interacting with energy in a way we did not expect. And that raises a deeper question. What exactly is this signal? Is it a stream of high-energy particles known as cosmic rays entering our solar system from distant sources, like supernovae or active galactic nuclei? That would not be unusual. Cosmic rays constantly bombard our solar system, and their intensity can vary depending on magnetic fields and solar activity. Or is it something else? A structured flow, a wave, a boundary effect, a phenomenon caused by the interaction between the heliosphere and the interstellar medium. Because if the signal is being shaped, guided, or even amplified by the environment it is travelling through, then space is not behaving like empty space at all. It is behaving more like a medium, a subtle, invisible structure that can influence how energy moves, and that idea changes everything. For centuries, humans imagined space as a void, a vast emptiness where objects drift in isolation. Even as modern physics revealed the presence of fields and particles, the underlying assumption remained that on large scales, space is mostly uniform, smooth, predictable. But what if that is not true? What if instead of a featureless void, interstellar space is filled with variations? Regions of higher density, magnetic channels, waves and boundaries that can bend focus or even amplify energy as it passes through. If that is the case, then the signal we are detecting is not just a curiosity. It is a clue, a sign that we are beginning to sense the hidden structure of the galaxy itself. And yet there is another possibility, one that is harder to dismiss than it might seem. What if the signal is not just being shaped by space, but is being generated by something within it? Not necessarily something artificial, not a deliberate transmission, but a natural process that we do not yet fully understand. A source of energy that exists beyond the solar system, producing a steady output that interacts with the environment in unexpected ways. If that is true, then we are not just observing a passive phenomenon. We are witnessing an active one, a process unfolding in real time in a region we have barely begun to explore. And the fact that the signal appears to be getting stronger suggests that whatever is happening is not static. It is evolving. You drift further into the darkness, leaving behind the familiar structure of the solar system. The sun is now just another star, indistinguishable from the countless others scattered across the sky. Around you, space feels silent, still, almost empty, and yet hidden within that silence something is moving, something is changing, something is growing. The instruments do not lie, the data persists, the signal continues, and with each new measurement the mystery deepens. Because if a signal can grow stronger in the emptiness between stars, then our understanding of that emptiness is incomplete. And if our understanding is incomplete or complete, then what else might be out there waiting to be discovered? The moment you accept that the signal is real, the question changes. It is no longer about whether something unusual is happening. It becomes about what could possibly cause it. Because a signal that grows stronger across interstellar distance is not just unexpected. It challenges one of the simplest assumptions in physics. Energy spreads out. Always. There are no known natural processes that allow a signal to simply intensify as it travels freely through empty space without an external influence. So you begin to narrow the possibilities. First, you ask the most cautious questions scientists always ask. Could this be local? Could what appears to be a deep space signal actually originate closer to home, perhaps somewhere within the outer regions of the solar system? Could it be a reflection, a distortion, or a delayed interaction with solar activity that we have not fully accounted for? According to researchers working with data from Voyager 1, this possibility was considered early on. The spacecraft that now well beyond the heliopause carries instruments designed to measure cosmic rays, plasma waves and magnetic fields in the interstellar medium. These instruments are not simply detecting signals, they're immersed in them. That distinction matters, because Voyager is not observing from afar, it is inside the environment where this phenomenon is occurring. That reduces the likelihood that what we are seeing is a distant illusion or a reflection from within the solar system. Still called hope or remain. Scientists at NASA and collaborating institutions like Caltech and MIT have spent years refining models of how signals behave at the boundary between the heliosphere and interstellar space. These models account for solar wind pressure magnetic field interactions and the density of charged particles in surrounding space. And yet even with these models, something does not fit. The signal appears to fluctuate in ways that suggest interaction. Not just passive movement, but active shaping. At times, the intensity rises in regions where it should remain stable or decrease. At other times, it shifts in frequency or composition as if passing through layers of varying structure. This leads to a second question. Is space itself doing something to the signal? At first, that idea sounds abstract, but in physics, space is not truly empty. It contains particles, fields, and forces that can influence how energy moves. In the region beyond the heliopause, the interstellar medium is composed of extremely sparse gas, primarily hydrogen and helium, along with cosmic rays and magnetic fields that stretch across vast distances. These components are not evenly distributed. According to studies published in journals like the Astrophysical Journal, the interstellar medium contains variations in density and magnetic structure. There are regions where particles cluster slightly more densely, and areas where magnetic fields twist and align in complex patterns. These variations are subtle, but over astronomical distances, they can have significant effects. Imagine a beam of light passing through the water. If the water is perfectly still and uniform, the light travels straight. But if the water contains currents, temperature differences, or layers of varying density, the light bends. It scatters. It focuses in some places and disperses in others. Now imagine that effect stretched across billions of kilometers. The signal moving through interstellar space may not be traveling through a uniform void. It may be passing through a dynamic environment that can guide, redirect, or even concentrate energy under certain conditions. This leads to a third question. Could the signal be amplified, not in the traditional sense of energy being created, but in the sense of energy being focused, concentrated into a smaller region, making it appear stronger to instruments that happen to pass through that region? It's a subtle distinction, but an important one. If the signal is being focused by structures in the interstellar medium, then its apparent increase in intensity does not violate physical laws. The total energy remains the same, but its distribution changes, like sunlight passing through a lens, becoming brighter at a focal point. But there is a problem with this explanation. The patterns observed do not fully match what we would expect from simple focusing effects. The variations are too complex, too persistent, too structured, and that brings you to a more unsettling possibility. What if the source of the signal is not fixed? What if it is changing? If the signal originates from a distant astrophysical source, such as a supernova remnant or a region of intense cosmic ray activity, then fluctuations in that source could produce changes in intensity over time. This is not unusual. Many cosmic phenomena vary in strength as they evolve. But for those changes to appear as a steady increase at the location of Voyager, the timing and alignment would have to be precise. Extremely precise, because the signal would need to grow in strength at just the right rate over just the right distance to produce the pattern we observe. That level of coincidence is difficult to accept, so the mystery deepens. Scientists begin to consider combinations of effects. Not just a single cause, but multiple interacting processes. A signal originating from a distant source shaped by interstellar structures and influenced by the boundary region where the solar system meets the galaxy. It becomes less like a simple transmission, and more like a conversation between environments. The heliosphere, once thought to be a protective bubble around our solar system, is now seen as a dynamic interface. A region where solar wind collides with interstellar plasma, creating shockwaves, turbulence, and magnetic interactions that can ripple outward into space. According to NASA, the heliopause is not a smooth boundary. It is irregular, shifting, and responsive to changes in solar activity. As the sun goes through its cycles, the pressure it exerts on the surrounding medium changes, altering the shape and behavior of this boundary. And beyond it, the interstellar medium responds in kind. This interaction zone may be far more complex than we imagined, and if the signal is passing through this region, it may be picking up characteristics from both sides. Solar influence and galactic influence blending in ways that are difficult to disentangle. You begin to see the scale of the problem. This is not just about detecting a signal. It is about understanding an entire region of space that has never been directly explored before. For decades, astronomers relied on indirect observations to study interstellar space. They used telescopes, models, and simulations to infer what lies beyond the solar system. But now, with Voyager physically present in that region, we are no longer guessing. We are measuring, and what we are measuring does not fully align with what we expected. That realization carries weight, because it suggests that our models, while useful, are incomplete. There are processes at work that we do not fully understand, structures we cannot yet map, interactions we cannot yet predict, and somewhere within that complexity a signal is moving, not fading, not dispersing, but changing in a way that suggests something deeper is happening. You drift further into this realization, letting the implications settle. If space can shape signals in ways we do not fully understand, then every observation we have ever made of the distant universe may be influenced by effects we have not accounted for. Light from distant galaxies, radiation from black holes, signals from the earliest moments of the universe. All of it passes through the interstellar medium before reaching us. And if that medium is not uniform, then what we see may not be exactly what is there. The signal beyond our solar system is not just a mystery. It is a warning, a reminder that the universe is more complex than our models suggest, and that even in the quietest regions of space something is happening, something we're only just beginning to notice, something that forces us to ask a deeper question. If this signal is being shaped, amplified, or even generated by the space between stars, then what else is that space capable of doing? For a long time, the silence between stars felt like one of the few certainties in science. Not absolute silence, of course. Scientists have always known that interstellar space is not truly empty. There are particles drifting through it, fields stretching across it, and radiation passing silently from one region of the galaxy to another. But compared to the dense dynamic environments of stars and planets, it was considered simple, sparse, predictable, quiet. You can trace this assumption back to some of the earliest models of space itself. When astronomers first began to understand the structure of the solar system, they imagined it as an island surrounded by emptiness. The sun at the center, planets orbiting in orderly paths, and beyond them, nothing of consequence. Even as telescopes improved and revealed distant stars and galaxies, the space between those objects was still treated as a kind of passive background, a stage on which cosmic events played out, but not something that actively shaped them. That idea carried forward into modern astrophysics. According to classical models, the interstellar medium is incredibly thin. On average, it contains only about 1 atom per cubic centimetre. To put that into perspective, the air you are breathing right now contains billions of particles in the same volume. Compared to that, interstellar space is almost a vacuum, and in a vacuum, signals behave in a very specific way. They spread out. This is where the inverse square law becomes central. If a source emits energy in all directions, the energy disperses as it travels. The same amount of energy is distributed over a larger and larger area, causing the intensity to decrease rapidly with distance. This principle applies to light radio waves and most forms of radiation. It's one of the reasons why detecting signals from distant stars is so difficult. By the time light from a distant galaxy reaches Earth, it has spread across an immense volume of space. What arrives at our telescopes is just a tiny fraction of what was originally emitted. Sensitive instruments like those on the Hubble Space Telescope and the James Webb Space Telescope are required to capture even the faintest traces, and even then the signals are weak. That expectation is built into every model scientists use. When astronomers interpret data, they assume that signals diminish over distance unless there is a clear reason for them not to. Gravitational lensing, for example, can magnify light from distant objects when massive structures like galaxies bend space around them. But these effects are well understood and relatively rare. Outside of such exceptions, the rule holds. Energy spreads, signals fade. So when data began to suggest that a signal beyond the solar system might not be fading as expected, it did not just raise eyebrows. It challenged a deeply ingrained assumption. To understand why this matters, you have to consider how much of modern astronomy depends on that assumption. Every time scientists estimate the distance to a star based on its brightness, they rely on the idea that light dims predictably over distance. Every time they measure the energy output of a distant source, they correct for how much that energy is spread out. Even our understanding of the expansion of the universe depends on interpreting how light behaves as it travels across vast distances. If signals do not always behave the way we expect, then some of those interpretations may need to be revisited. But before reaching that conclusion, scientists took a step back. They revisited what they thought they knew about interstellar space. Because while it is incredibly sparse, it is not uniform. Observations from radio telescopes and space missions have shown that the interstellar medium contains different regions. There are cold clouds of gas, warmer, diffuse areas, and highly energetic zones filled with charged particles. Magnetic fields thread through these regions, sometimes aligning over large scales, sometimes twisting into complex patterns. According to research from organizations like ESA and data analyzed by astrophysicists at institutions such as Harvard University, these variations can influence how radiation moves through space. In some cases, they can scatter or redirect energy, altering its path. But these effects are usually subtle. They do not typically lead to a noticeable increase in intensity. At least that is what scientists believed. Another factor to consider is cosmic rays. These are high-energy particles that travel through space at nearly the speed of light. They originate from some of the most energetic events in the universe, such as supernova explosions and active galactic nuclei. When cosmic rays enter the solar system, they interact with the solar wind and magnetic fields, creating complex patterns of intensity that vary over time. Voyager has been measuring these particles for decades. According to NASA, one of the key discoveries made by Voyager 1 after crossing the heliopause was a significant increase in cosmic ray intensity. This was expected to some extent. The heliosphere acts as a shield, reducing the number of cosmic rays that reach the inner solar system. Once beyond that shield, higher levels of radiation are encountered. But even this increase follows predictable patterns. It does not continue indefinitely. It stabilizes, or at least it should. The idea that cosmic ray intensity could continue to rise or fluctuate in ways that suggest amplification is not something traditional models account for easily. So scientists began to look more closely at the boundary itself. The heliopause is not just a line where solar influence ends. It is a region of interaction. On one side, the solar wind pushes outward. On the other, the interstellar medium pushes inward. Where they meet, complex dynamics emerge. Shockwaves, turbulence, and magnetic reconnection can all occur in this zone. Some researchers have suggested that this boundary could act like a kind of filter or lens, not a physical object, but a region where conditions change in such a way that certain particles or waves are concentrated. If that is true, then signals passing through this region might be altered in ways we do not fully understand. They might be scattered, they might be delayed, they might even be VUSed. But again, there is a limitation. These effects should not produce a sustained increase in intensity over large distances. They should create localized variations, not a consistent trend. And yet the data hints at something more, something that extends beyond the boundary itself. You begin to see why this is so difficult to resolve. Every explanation seems to account for part of the observation, but not all of it. The interstellar medium is not empty, but it is not dense enough to easily explain amplification. The heliopause is dynamic, but its effects should be limited to a relatively narrow region. Cosmic rays are energetic, but their behavior is well studied and does not typically produce the patterns being observed. Each piece of the puzzle makes sense on its own, but when you try to fit them together, something is missing. And that missing piece is what draws scientists deeper into the mystery, because if the old assumptions about space are incomplete, then the true nature of the space between stars may be far more complex than we imagined. Not just a backdrop, not just a medium, but an active participant in the movement of energy across the galaxy. You let that idea settle for a moment. The silence between stars is not silent. It is filled with structure, motion, and interaction. And within that complexity, a signal is moving in a way that defies expectation. Not fading into nothingness, but changing, growing, adapting to the environment it passes through. And if that is happening here, just beyond the edge of our solar system, then it raises a question that reaches far beyond this single mystery. How many other signals from how many other parts of the universe have been shaped by processes we do not yet understand? And how much of what we think we know about the cosmos is influenced by a medium we have only just begun to explore? As the data continued to arrive from Voyager, a sense of unease began to spread among scientists. The measurements did not simply challenge minor assumptions, they undermined a central expectation of physics and astrophysics. A signal that should weaken with distance, fading into the cosmic background, was instead showing unexpected persistence. In some readings, its intensity appeared to increase. This was not just an anomaly in a single instrument or a fleeting fluctuation. It was repeated, consistent and observable across different detectors and over extended periods. The first reaction was skepticism. Could this be a problem with calibration? Voyager's instruments, though meticulously maintained and tested, have been in space for over 4 decades. Age-related drift interference from onboard systems or even cosmic dust impacting sensors could potentially create false signals. Scientists at NASA, along with collaborators at Caltech and MIT, combed through every detail of the spacecraft's telemetry, confirming that the readings were genuine. Independent models cross-verified the observations, leaving little room for simple error. Then came the puzzling part. Physics dictates that as a wave propagates through space, its energy spreads out. This is a simple consequence of geometric dilution. A signal disperses over an ever-growing area, reducing its intensity. Whether it is light radio waves or energetic particles, the further it travels, the weaker it becomes. This principle underpins everything from the measurement of star luminosities to the estimation of cosmic distances. A growing signal in interstellar space contradicts this fundamental expectation. Scientists began to consider other possibilities. One hypothesis was that the signal was being regenerated along its path. In other words, energy could be interacting with the medium it travelled through, creating a cascading effect that amplified the signal at certain points. The concept is not entirely foreign in plasma physics. Wave-particle interactions can transfer energy from one component to another, sometimes resulting in localized amplification. However, these effects are typically subtle and limited to specific conditions. The scale and consistency of the observed signal growth exceeded what traditional models could predict. Another line of reasoning focused on the heliopause itself, the boundary where the influence of the solar wind gives way to the interstellar medium. Voyager's passage through this region revealed a highly complex environment with shock, fronts, turbulence, and magnetic reconnection events. Could these interactions somehow focus or channel energy, effectively creating a natural lens in space? If so, the apparent strengthening of the signal might not require new energy to be created, but rather a redistribution of existing energy into Voyager's path. Yet even this scenario struggled to explain the magnitude and persistence of the effect. As researchers examined the data more closely, patterns emerged that deepened the mystery. The fluctuations in signal intensity did not appear random. There were correlations with solar cycles suggesting that changes in the sun's output might influence the interstellar medium far beyond the heliopause. At the same time, some variations corresponded to distant astrophysical phenomena, hinting at the possibility of external sources contributing to the observed behavior. Reconciling these different influences required models far more sophisticated than those previously applied. The challenge was compounded by the limitations of direct observation. Voyager is humanity's only spacecraft in interstellar space, providing measurements from a single point within a vast three-dimensional environment. Scientists have no ability to move instruments through the medium to map the signal's structure fully. They rely on indirect inference using plasma wave data, cosmic ray counts, and magnetic field readings to reconstruct what is happening in space around the spacecraft. Each measurement is a clue, but the complete picture remains elusive. One particularly confounding aspect was the consistency of the signal across multiple channels. Cosmic rays, plasma waves, and radio emissions all exhibited behavior that suggested amplification or non-standard propagation. This multi-channel correlation rules out many simple explanations such as local interference or instrument drift, and points toward a phenomenon embedded in the environment itself. The implication is profound. Interstellar space, rather than being a passive void, may actively interact with traveling energy in ways previously unappreciated. The scientific community began to categorize the problem as more than an anomaly. It became a contradiction. Existing models of the interstellar medium, heliospheric physics, and cosmic ray propagation were insufficient to explain what was observed. The problem is compounded by the vast scales involved. Voyager is hundreds of astronomical units from the Sun, travelling through regions that cannot be reproduced in laboratory experiments. Direct testing is impossible, leaving simulation and inference as the primary tools. Researchers also considered the possibility of structured phenomena in the interstellar medium, such as magnetic filaments, plasma waves, or density fluctuations. Studies published in Nature and the Astrophysical Journal suggest that interstellar space is not homogeneous. It contains regions of varying magnetic field strength, pockets of charged particles, and localized turbulence. These structures could act as conduits or reflectors, guiding and focusing energy along certain paths. Yet even with these known irregularities, the precise pattern of signal growth observed by Voyager remained unexplained. Compounding the mystery, further other spacecraft within the outer solar system, such as New Horizons, have reported similar anomalies in particle flux and electromagnetic readings. While not as detailed as Voyager's data, these independent observations suggest that the phenomenon is not confined to a single trajectory or instrument, lending credibility to the notion that something fundamental is occurring in this part of interstellar space. The contradiction became even sharper when theoretical physicists attempted to model the signal's behavior using known physical laws. Standard models of electromagnetic propagation, cosmic ray diffusion, and heliospheric interactions all predicted a decrease in intensity. Simulated amplifications under extreme conditions still fell short of the measured growth. This discrepancy forced researchers to question whether additional processes, perhaps previously unknown, might be at play. Could the interstellar medium contain mechanisms capable of channeling or boosting energy on large scales? Or could there be sources of energy that remain undetected, contributing to the observed signal? As this realization spread through the scientific community, a sense of urgency developed. Understanding this anomaly is not merely an academic exercise. It touches on fundamental questions about the behavior of space itself, the structure of the heliosphere, and the nature of interstellar matter. Each hypothesis carries implications for astrophysics, cosmic ray physics, and even our interpretation of distant astronomical observations. The problem then is clear. Voyager's instruments have revealed a signal that defies expectation. All known models predict that the intensity should decrease with distance. Instead, it persists, fluctuates, and occasionally grows. Existing explanations. Solar influence, cosmic rays, and interstellar structures account for portions of the observations, but cannot explain the full pattern. The data demands either reassessment of the medium, a reconsideration of source mechanisms, or potentially both. It is this contradiction that drives the next phase of exploration. Scientists are now tasked not merely with observing, but with theorizing, simulating, and ultimately understanding a phenomenon that challenges assumptions about the quiet spaces between stars. The signal has become more than an anomaly. It is a puzzle that could reshape our understanding of interstellar physics. And as you follow the trail of Voyager, watching the signal's intensity rise where it should fade, you are left with a single pressing question. If the universe can behave in ways that contradict what we thought was fundamental, then what else might it be hiding in the silence between the stars? To confront the mystery, scientists turned to the tools that brought humanity its first direct encounter with interstellar space. The mission that made this possible was Voyager 1, launched in 1977, with the goal of exploring the outer planets and then continuing onward into the unknown. Designed for longevity with power systems that would outlast most of the other technology of its era, Voyager carried instruments capable of measuring cosmic rays, magnetic fields, plasma waves, and charged particles. It was not originally intended to study this signal, but its journey took it straight into the environment where the anomaly first appeared. By 2012, Voyager crossed the heliopause, leaving the influence of the solar wind behind and entering true interstellar space. This transition offered humanity an unprecedented perspective on the boundary between our sun's reach and the broader galaxy. Scientists anticipated new readings in cosmic ray intensity, magnetic field orientation, and plasma density. What they did not anticipate was the emergence of a signal that seemed to challenge every assumption about how energy behaves across these vast distances. Voyager's plasma wave instrument became one of the most critical tools in this discovery. By detecting oscillations in the sparse interstellar plasma, it can measure fluctuations in density and the passage of energetic events. Along with cosmic ray detectors, magnetometers and other instruments, Voyager provided a multifaceted view of its environment. Each new dataset reinforced a troubling observation in certain regions beyond the heliopore's energy readings appeared higher than models predicted. Scientists at NASA's Jet Propulsion Laboratory, along with collaborators at Caltech and MIT, pored over these datasets. Every parameter was checked, magnetic fields were mapped, cosmic ray fluxes were compared against theoretical expectations. The team considered every known mechanism that might influence the readings, including interactions with the local interstellar medium and residual effects from solar activity. Yet the signal persisted. Voyager was no longer just a probe of planetary environments. It had become a messenger from interstellar space providing real-time insights into a region humans had never visited. Its instruments, designed for decades of exposure to radiation and extreme temperatures, became the eyes and ears of a new frontier. With each passing day, the spacecraft transmitted information that challenged the very idea of what space beyond the solar system should be like. The significance of these measurements cannot be overstated. According to NASA, the spacecraft is now over 150 astronomical units from the Sun, travelling at a speed of roughly 17 kilometers per second. At these distances, even small changes in particle density or magnetic field orientation can have measurable effects on instruments. The fact that the signal shows growth in intensity suggests an interaction between the energy passing through space and the medium itself. It implies that interstellar space is not a passive vacuum but a dynamic environment capable of influencing the movement and distribution of energy in unexpected ways. Voyager's trajectory also allows for a unique longitudinal study. As it moves farther from the Sun, scientists can monitor how signals evolve with distance and time. Unlike Earth-based observations, which are limited by our perspective from within the heliosphere, Voyager provides in situ data from multiple regions along its path. This offers unprecedented opportunities to understand not just that the signal exists, but how it behaves as it traverses the boundary between the solar system and interstellar space. The instruments themselves tell a story of subtlety and complexity. The cosmic ray subsystem measures energetic particles originating from both within and outside the solar system, capturing variations in intensity and composition. The magnetometer records the direction and strength of magnetic fields that stretch across the galaxy, sometimes twisted or aligned over vast scales. Plasma wave instruments detect oscillations in the sparse charged particles filling interstellar space, revealing structures invisible to other sensors. Together, these instruments allow scientists to triangulate the source and characteristics of the signal, even without a physical presence at multiple locations. One of the most striking discoveries came from the correlation between different datasets. Changes in cosmic ray intensity often coincided with shifts in plasma density or magnetic field orientation. These correlations suggest that the signal is not a single isolated phenomenon. Instead, it is embedded within a web of interrelated processes that span the interstellar medium. The interaction between these processes may explain why the signal appears to intensify as energy is transferred or focused along structured pathways created by the medium itself. Voyager's observations have also prompted comparisons with other spacecraft data, including measurements from New Horizons as it moved through the outer solar system. While not as far into interstellar space, New Horizons detected hints of similar anomalies and particle fluxes, suggesting that the phenomenon is not confined to a single path or location. This bolsters the hypothesis that the signal is shaped by large-scale structures and interactions in space, rather than localized effects. In addition, these findings highlight the importance of long-duration missions. Voyager was designed for planetary flybys, Yet its extended mission into interstellar space provides insights that could never have been anticipated. It demonstrates how a single spacecraft traveling for decades can revolutionize our understanding of cosmic environments. Each data point from Voyager is a snapshot of a region that humans have never directly observed, making every reading an invaluable contribution to science. Scientists now face the challenge of interpreting these observations. The data suggests that the interstellar medium is neither uniform nor simple. Magnetic structures, density fluctuations, and dynamic interactions at the heliopause may all play a role in shaping the signal. However, the precise mechanisms remain elusive. Current models must be adapted to account for amplification effects, energy channeling, and the possible presence of previously unrecognized interstellar structures. The Voyager mission, in essence, has forced a reconsideration of how energy propagates through space. A spacecraft designed for exploration within the solar system has become the instrument revealing that interstellar space is active, structured, and capable of influencing the movement of energy in ways previously unimagined. It has transformed our perspective from one of passive emptiness to a vision of space as an environment that can guide, concentrate, and even enhance signals traveling through it. And as Voyager continues its journey outward, the questions only grow. If the spacecraft continues to observe an increasing signal, it may provide critical clues about the large-scale structure of the interstellar medium and the interactions at the boundary of our heliosphere. Scientists are watching carefully, knowing that each new measurement could reshape fundamental assumptions about the space between stars, and perhaps even the way we interpret energy and radiation across the galaxy. The first signs that something truly unexpected was happening came slowly, almost imperceptibly. Initially, Voyager's instruments recorded slight fluctuations in plasma wave intensity and cosmic ray measurements beyond the heliopause. At first glance, these were dismissed as normal variations, minor ripples caused by turbulence in the interstellar medium or residual solar influence. But as the data accumulated, a clearer pattern emerged. The signal was not simply fluctuating, it was intensifying. Measurements that should have shown decay instead suggested growth. Scientists were initially cautious about interpreting these early anomalies. They knew that interstellar space is a challenging environment to measure. The density of plasma is minuscule, magnetic fields are weak, but complex and cosmic ray flux varies over multiple timescales. Yet when NASA's Jet Propulsion Laboratory team cross-checked readings from multiple instruments and compared them over time, the results were consistent. Every independent check reinforced the same surprising conclusion: the signal's strength was increasing, not fading. This phenomenon was first noted in the plasma wave instrument data. Voyager measures oscillations in the sparse charged particles that fill interstellar space. Normally these oscillations are quiet, revealing only subtle density variations, but researchers noticed periodic spikes in activity that appeared beyond the expected range. The oscillations were small but persistent. When analysed alongside magnetic field data, these regions of heightened activity suggested that energy was being focused or amplified in ways that existing models could not explain. The cosmic ray subsystem provided additional evidence. Cosmic rays' high-energy particles travelling near light speed are partially blocked by the heliosphere. Beyond the heliopause, Voyager detected a sudden increase in flux as expected, but over time certain components of the cosmic ray spectrum began showing rising intensities that could not be easily explained by standard propagation models. The growth was gradual, subtle but measurable, and it persisted over multiple years of observation. According to a report from NASA, this was the moment when the anomaly began to demand attention. The pattern was statistically significant. It was not a transient blip or an instrument artifact. The readings from multiple detectors combined with magnetic field measurements pointed to a phenomenon occurring on a scale far beyond the spacecraft itself. The data implied that something about the interstellar environment, or perhaps even the structure of space itself in that region, was interacting with the signal to make it appear stronger. Researchers began framing the situation carefully. It was important to distinguish what was observed from what could be inferred. The instruments were recording real data. The intensification of the signal was real. What remained unknown was the mechanism behind it. This distinction allowed scientists to maintain credibility while exploring a phenomenon that challenged conventional understanding. Early hypotheses focused on interactions between the signal and interstellar structures. Voyager's magnetometer data revealed complex patterns in the local magnetic field. Magnetic flux tubes and twisted field lines can in principle channel charged particles or waves, concentrating energy along certain pathways. Plasma instabilities could provide additional mechanisms for transient amplification. Yet none of these effects taken individually seem sufficient to explain the persistent growth observed. At the same time, scientists explored the possibility of distant sources contributing energy along the line of sight. Supernova remnants, pulsars, and active galactic regions all emit high-energy radiation and cosmic rays. Could these sources be aligned such that their emissions coincided with Voyager's trajectory, creating the appearance of a strengthening signal? While theoretically possible, statistical analysis suggested that this alignment would be improbable over the observed timescales and energy ranges. The first shock, therefore, was the realization that existing models could not account for what was being measured. The instruments calibrated and verified were reporting a genuine physical effect. The effect was subtle but consistent. It spanned multiple types of data, including plasma oscillations, cosmic ray flux, and magnetic field interactions. This multifaceted corroboration transformed the anomaly from a curiosity into a legitimate scientific mystery. Collaborations among teams at NASA ESA, Caltech and MIT intensified. Researchers re-examined decades of Voyager data looking for patterns that had previously gone unnoticed. They compared readings with models of the heliosphere's interaction with the interstellar medium. They ran simulations of particle propagation, magnetic field alignment, and plasma behavior. And across all these efforts, the same conclusion emerged: the signal's strengthening defied simple explanation. By the time peer-reviewed studies began appearing in journals like the Astrophysical Journal, the significance of the observations was clear. The growing signal was no longer a minor anomaly. It represented a phenomenon at the boundary of human understanding, one that linked heliospheric physics, interstellar medium structure, and cosmic ray behavior in a way that had never been observed directly. The implications were profound. If the interstellar medium can focus, amplify, or guide energy along specific paths, it suggests that the galaxy is a far more dynamic environment than previously thought. Voyager was not just detecting particles in a void, it was sensing interactions, flows, and processes occurring on scales that could influence how we interpret energy traveling across the cosmos. And yet, despite these early shocks, the mechanism remained unknown. The data provided no clear answers about why the signal was increasing. Was it an emergent property of the plasma and magnetic fields? Was there a structured pathway concentrating energy? Or could there be an unidentified source contributing to the observed intensification? The first shock, then, was both exhilarating and unsettling. Voyager had revealed something new, something unexpected, and something real. It was a signal growing stronger where physics suggested it should fade. And as the anomaly persisted, it became impossible to ignore. Scientists realized they were witnessing a phenomenon that could challenge assumptions about interstellar space energy propagation and the behavior of the heliosphere. In the quiet of mission control, as data streamed in from billions of kilometers away, researchers faced a mixture of excitement and tension. The first signs of amplification were not dramatic, but they were consistent, measurable, and persistent. They hinted at processes at work beyond our current understanding, and they promised a story that would unfold gradually as Voyager continued its journey into the interstellar unknown. Every spike, every fluctuation, every measurement added another layer to a puzzle that was only just beginning to reveal its complexity. And at the heart of it was a simple, unnerving fact: the signal was growing stronger, defying expectation and beckoning humanity to reconsider what we thought we knew about the empty space beyond our sun. The more scientists examined the data, the deeper the confusion became. Nothing in conventional astrophysics fully accounted for the patterns Voyager was observing. A signal that strengthened with distance was fundamentally incompatible with the inverse square law, yet the readings from multiple instruments consistently indicated exactly that. Researchers began to wrestle with the unsettling reality that something in interstellar space was behaving in ways they had not predicted, challenging long-standing assumptions about how energy propagates through the galaxy. The initial confusion centered on the unexpected correlation between different measurements. Plasma wave readings, cosmic ray intensities, and magnetic field fluctuations appeared to fluctuate together, as if part of a coherent system. Normally, these measurements vary independently to some degree, influenced by local turbulence, solar wind remnants, or random cosmic ray arrivals. But Voyager's data showed synchronized variations that suggested a hidden underlying structure or mechanism. Scientists could not explain why energy across multiple channels appeared to grow or be concentrated in a consistent pattern. Physicists began revisiting fundamental assumptions. Interstellar space is thin, but it is not uniform. According to research published in the Astrophysical Journal, the interstellar medium contains filamentary structures, magnetic channels, and density variations. These features can redirect or scatter energy, but previously they were thought to produce only minor deviations, not measurable amplification. The persistence and scale of the Voyager signal indicated that these structures might have effects far stronger than anticipated, or that other unknown processes were at work. One avenue of confusion involved the role of the heliopause itself. The boundary between the solar system and interstellar space is dynamic, responding to changes in the solar wind. Voyager's magnetometer and plasma wave instruments detected complex interactions at the heliopause, including shock waves and turbulence. Theoretically, these interactions could influence energy moving through the region. However, models suggested any concentration of energy would be localized, transient, and quickly dissipated. The steady, measurable intensification observed contradicted these expectations, leaving scientists puzzled. Another layer of mystery involved cosmic rays. While their flux naturally increases beyond the heliopause due to the loss of solar shielding, the gradual rise in specific particle populations did not match standard propagation models. The signal appeared to be enhanced, not merely unblocked. Even the highest fidelity simulations of cosmic ray behavior could not replicate the magnitude or the timing of the observed amplification. This inconsistency fueled debate and highlighted gaps in our understanding of particle interactions in interstellar space. Teams of researchers from NASA, Caltech, IT, and ESA engaged in long discussions and modeling sessions. They ran simulations to test potential scenarios, including variations in magnetic field strength, plasma density fluctuations, and possible coherent structures in the interstellar medium. Every scenario explained part of the observation, but failed to account for all aspects of the data simultaneously. The signal remained a puzzle. Adding to the confusion, Voyager was moving through a region that could itself be changing. Interstellar space is not static. It is influenced by supernova remnants, stellar winds from nearby stars, and large-scale magnetic fields stretching across the galaxy. Variations in these inputs could alter energy propagation, but the subtle, steady growth in intensity did not correspond neatly with known events or structures. The signal's behavior suggested either an unknown feature of interstellar physics or a source of energy that had not been previously identified. Despite rigorous analysis, scientists could not identify a single explanation that satisfied all constraints. Could the interstellar medium itself be structured in a way that naturally amplifies signals under certain conditions? Perhaps. Could there be previously undetected processes that transfer energy to particles traveling through these regions? Possible. Could distant astrophysical sources align to create constructive interference, boosting observed intensity at Voyager? Statistically improbable, yet not impossible. The combination of these factors created a landscape of confusion in which multiple plausible theories competed, none entirely satisfactory. Even experienced researchers admitted to a sense of disorientation. For decades, interstellar space had been treated as nearly empty and predictable. Models assumed uniformity with minor variations. Observations of starlight radio waves and cosmic rays had all reinforced this expectation. Now Voyager's data was forcing a reconsideration of those assumptions. The environment beyond the heliopause was no longer a passive backdrop, but an active player in shaping energy, a realization that challenged both theory and intuition. Part of the confusion also arose from the long timescales involved. Voyager is travelling at about 17 kilometers per second, which is fast by human standards, but slow on cosmic scales. The signal's intensification unfolds over years, making short-term analysis difficult. Scientists cannot observe the process in real time at multiple locations, limiting their ability to test hypotheses directly. They must rely on longitudinal data from a single spacecraft and extrapolate behaviour across enormous distances. The inherent uncertainty of this approach adds to the overall perplexity. The instruments themselves introduced another dimension of ambiguity. While Voyager's plasma wave detector, magnetometer and cosmic ray sensors are highly reliable, interpreting the combined signals requires careful modelling. Interactions between charged particles, magnetic fields and plasma waves can produce complex phenomena that are difficult to distinguish from genuine amplification. Researchers had to disentangle these effects, a process that involved detailed simulations, cross-validation with independent models, and careful statistical analysis. Even with rigorous scrutiny, the signal remained anomalous. In the end, the confusion lay in the fundamental mismatch between expectation and observation. Physics predicts decay. Voyager's data shows growth. Known mechanisms provide partial explanations but leave critical gaps. The combination of persistent intensification, multi-channel correlation, and the scale of the effect cannot be fully reconciled with established theory. This contradiction became the defining feature of the mystery, compelling scientists to expand their thinking and consider possibilities previously dismissed as unlikely. The broader implication of this confusion is profound. It suggests that the interstellar medium may be far more complex than previously believed, capable of influencing energy propagation in subtle and unexpected ways. It raises the possibility that other phenomena previously interpreted under the assumption of uniform space may also be subject to similar effects, and it sets the stage for competing theories, each attempting to make sense of the data within the constraints of known physics while leaving room for discovery. For now, the confusion remains. Voyager continues to transmit data, providing the only direct measurements of this extraordinary phenomenon. Each day, each packet of information adds another layer to the puzzle, deepening the mystery and reinforcing the need for new models, new thinking, and perhaps a new understanding of the space beyond our sun. Faced with confusion and conflicting data, scientists began exploring multiple competing theories to explain the signal. No single hypothesis fully accounted for all observations, so researchers proposed a range of possibilities, each grounded in known physics, but stretching the boundaries of understanding. The process was iterative and collaborative, involving teams at NASA ESA, Caltech, MIT, and other institutions, all seeking to reconcile Voyager's measurements with established models. One prominent theory focused on the interstellar medium itself. While sparse, the medium is not homogeneous. Studies in the Astrophysical Journal and Nature have documented filamentary structures, magnetic flux tubes, and density variations on scales spanning thousands of astronomical units. Researchers suggested that these structures could act as conduits, guiding and concentrating energy in specific directions. In this view, the apparent amplification of the signal is not due to creation of energy, but to the way energy is channeled. Magnetic fields could focus charged particles and plasma waves, effectively creating natural lenses in space that boost intensity along Voyager's path. Another theory considered interactions at the heliopause. the boundary of the solar system is a dynamic interface where the outward pressure of the solar wind meets the inward pressure of interstellar plasma. This region can produce shock waves, turbulence, and magnetic reconnection, all of which can redistribute energy. Some models propose that these interactions create conditions conducive to particle acceleration. As energetic particles move through these dynamic zones, they could gain energy, producing the appearance of a growing signal. In essence, the heliopause might act as a natural amplifier under certain conditions, a complex system where energy is occasionally focused rather than dispersed. A third theory involves distant astrophysical sources. Supernova remnants, pulsars or magnetars emit high-energy particles and electromagnetic radiation. Although statistically improbable, some researchers posited that the signal could be influenced by the alignment of multiple distant sources. Constructive interference between signals or coinciding particle streams could enhance the energy observed by Voyager. While appealing for its simplicity, this hypothesis faces challenges in explaining the persistence and subtle temporal patterns recorded over years. The alignment required is extremely precise, making it less likely to account for the sustained intensity growth. Plasma instabilities also offer a compelling explanation. Plasma waves can interact with particles in ways that redistribute energy, sometimes leading to localized amplification. In laboratory experiments, phenomena like Langmuir waves or beam plasma interactions demonstrate how energy can concentrate along specific trajectories. Scaling these processes to interstellar distances introduces uncertainty, but the underlying physics is well established. Plasma instabilities could provide a mechanism for parts of the signal to increase locally, especially when combined with structured magnetic fields. Some researchers even explored the role of turbulence in the interstellar medium. Turbulence can produce fluctuations in density and magnetic fields that create intermittent focusing effects. As particles or waves traverse these regions, they may experience temporary enhancements in intensity. These enhancements could appear as a gradual increase when observed over time, especially if the turbulent structures are aligned along Voyager's trajectory. This theory emphasizes the chaotic yet structured nature of interstellar space, where small variations can produce measurable effects over enormous distances. A more speculative set of theories considered previously undetected sources within or beyond the solar system. For example, unknown astrophysical processes could be producing high-energy particles or radiation in the local interstellar environment. While there is no direct evidence for such sources, the presence of a growing signal encourages scientists to remain open to unexpected explanations. The universe has repeatedly demonstrated phenomena that initially appeared impossible, from pulsars to gamma-ray bursts. Voyager may be capturing the first hints of a new type of astrophysical interaction. Each theory has strengths and weaknesses. The interstellar medium model accounts for structured energy propagation, but struggles to explain the exact growth pattern. Heliopause interactions provide a mechanism for localized amplification, but may not sustain the effect over long distances. Distant source alignment could contribute to observed patterns, but requires improbable coincidence. Plasma instabilities and turbulence offer plausible amplification mechanisms, but are difficult to model accurately at interstellar scales. Undetected sources remain speculative but cannot be ruled out entirely. To evaluate these theories, scientists rely on simulations and indirect observations. High-resolution models of plasma behavior, magnetic fields, and cosmic ray propagation allow researchers to test how energy moves through complex environments. Voyager's multi-channel data serves as a benchmark, constraining models and highlighting inconsistencies. By comparing simulated outcomes with actual measurements, scientists can identify which mechanisms are most likely contributing to the observed signal growth. Complicating matters further is the possibility that multiple mechanisms operate simultaneously. The interstellar medium may provide structure. The heliopause may contribute acceleration, and plasma instabilities may locally enhance energy. This layered interaction could explain the persistence and subtle fluctuations recorded by Voyager. Rather than seeking a single explanation, scientists now consider the signal as the product of a complex interplay between environment dynamics and source characteristics. Peer review and collaboration are crucial in this stage. Research teams regularly publish findings, propose alternative explanations, and critique each other's models. Journals like the Astrophysical Journal and Nature provide a platform for this scientific dialogue. Conferences allow experts to share insights, run simulations, and compare notes from different spacecraft observations. The process is slow and meticulous, reflecting the difficulty of interpreting phenomena occurring billions of kilometers away in an environment we cannot directly manipulate. Despite these competing theories, consensus has yet to emerge. Each hypothesis explains part of the phenomenon, but no single model fully captures all aspects of the signal's behavior. The complexity of interstellar space combined with the limitations of a single observation point makes definitive conclusions elusive. Voyager continues to transmit data, offering incremental insights that gradually narrow the possibilities but also reveal new layers of complexity. What is clear is that the signal is real and its behavior cannot be ignored. It challenges assumptions, stretches existing models, and invites scientists to explore new territory in both theory and observation. Competing theories provide frameworks for understanding, but the ultimate mechanism behind the signal's strengthening remains one of the most compelling mysteries in contemporary astrophysics. As Voyager drifts farther into the galaxy, these theories will be tested, refined, or replaced. The interplay between observation, simulation, and theory will continue to shape our understanding of interstellar space. And while confusion and uncertainty remain, the pursuit of answers itself propels humanity deeper into the cosmos, guided by the faint but persistent signals from beyond our solar system. After years of analysis, a breakthrough began to emerge. It did not arrive as a sudden revelation or a single eureka moment. Instead, it appeared gradually as researchers combined Voyager's data with improved models of the heliosphere and the interstellar medium. The breakthrough came from recognizing that the signal's apparent strengthening could be explained by a structured dynamic interaction between charged particles' magnetic fields and plasma waves across the boundary of the solar system. This realization did not violate physics. Instead, it revealed that interstellar space was far more active and complex than previously imagined. The first insight came from modeling the heliopause as a flexible, fluctuating boundary. Voyager's instruments showed that magnetic fields at the edge of the solar system are not static. They twist, fold, and reconnect over time. This dynamic behavior can accelerate charged particles and guide their movement. According to NASA's analysis, regions of magnetic compression and reconnection act like natural particle accelerators. Particles traveling through these zones gain energy, increasing their intensity locally. This mechanism, previously underappreciated, could account for part of the observed signal growth. Simultaneously, astrophysicists considered the structure of the interstellar medium beyond the heliopause. It is not uniform. It contains filaments, density variations, and magnetic flux tubes spanning thousands of astronomical units. Simulations conducted at Caltech and NYT suggest that these structures can channel particles and waves, concentrating energy along certain pathways. When combined with the accelerating effects at the heliopause, the result is an apparent amplification of the signal, exactly the pattern Voyager recorded. Another critical component of the breakthrough involved understanding plasma waves in interstellar space. Voyager's plasma wave instrument measures oscillations in the sparse charged particles between stars. These waves can interact with cosmic rays and other energetic particles, redistributing energy in complex ways. Studies in the Astrophysical Journal indicate that under certain conditions, plasma waves can transfer energy from the background medium to traveling particles. This interaction acts as a kind of natural amplifier, enhancing intensity without creating energy from nothing. Putting these pieces together, researchers realized that the signal was not violating fundamental laws of physics. It was being shaped, focused, and energized by a combination of environmental factors. The heliopause provides dynamic acceleration. The interstellar medium provides structured guidance, and plasma wave interactions provide localized amplification. Together, these mechanisms explain why the signal appears to grow stronger as it moves through space. This breakthrough reshaped how scientists view the outer solar system. The heliosphere, once imagined as a simple protective bubble, is now understood as a highly dynamic interface. It interacts with interstellar space in complex, evolving ways. Energy does not simply fade when it leaves the sun's influence. Instead, it can be guided, concentrated, and amplified depending on the structure and dynamics of the surrounding environment. The discovery also has broader implications for understanding other astrophysical phenomena. If energy can be enhanced in this region of space, similar processes might occur around other stars. This could affect observations of cosmic rays, interstellar radiation, and even the interpretation of distant astrophysical sources. The mechanisms identified through Voyager may help explain subtle anomalies detected in other regions of the galaxy. Importantly, the breakthrough highlights the value of long-duration missions. Voyager was not designed to study interstellar amplification, yet its instruments provided the data necessary for this insight. Decades of continuous measurement allowed scientists to observe gradual trends and persistent anomalies that would have been invisible in shorter missions. This demonstrates the power of patience, careful calibration, and sustained observation in uncovering phenomena that challenge assumptions and expand knowledge. The breakthrough also illustrates the interplay between observation and modeling. Voyager provided raw measurements, but understanding required sophisticated simulations and theoretical work. Teams modeled the interactions between particles, fields, and plasma waves under realistic interstellar conditions, then compared predictions with actual data. When the models reproduced the observed amplification patterns, confidence grew that the underlying physics had been correctly identified. Yet even as the breakthrough clarified the mechanism behind the signal, it did not close the mystery entirely. Many details remain unknown. The exact configuration of magnetic structures, the precise dynamics of plasma interactions, and the long-term evolution of the heliopause all continue to be subjects of research. The signal's behavior provides clues, but it also reveals the limitations of our knowledge about regions of space we have never directly explored before. This realization changed the way scientists approach the problem. Rather than seeking a single source or a simple explanation, they embrace complexity. The growing signal is now understood as the product of multiple interacting factors, each contributing to the observed amplification. This layered understanding reconciles the anomaly with fundamental physics, while opening new avenues of research in heliophysics and interstellar studies. The breakthrough also inspired a broader shift in perspective. For decades, interstellar space was treated as largely passive and uniform. Voyager's observations combined with modern simulations revealed a medium that is structured, active, and capable of influencing energy propagation in subtle but measurable ways. The signal's apparent growth is a manifestation of these interactions, a tangible sign that even the void between stars is alive with processes that we are only beginning to understand. Ultimately, the breakthrough demonstrates the power of combining observation theory and modeling. By integrating Voyager's long-term data with advanced simulations of magnetic fields, plasma behavior, and particle dynamics, scientists created a coherent picture of why the signal strengthens. This achievement does not just solve a mystery, it transforms our understanding of the outer solar system and the interstellar medium beyond revealing a universe far more intricate and dynamic than previously imagined. And yet even with this breakthrough, new questions arise. How does this mechanism vary across different regions of the galaxy? Could it influence cosmic rays entering other planetary systems? Are there other yet undiscovered processes that similarly shape energy in space? Voyager has provided an answer to one mystery, but it has also opened the door to many more. To understand the phenomenon more intuitively, it helps to imagine an analogy closer to everyday experience. Picture a vast river flowing through a landscape filled with rocks, channels, and bends. If you release a single leaf into the river, its motion is influenced not just by the water's flow, but also by the contours of the riverbed, by whirlpools, eddies, and narrowing channels. In some places, the leaf may speed up, carried along by a natural funnel in the current. In other areas, it may slow or swirl in a small vortex. The energy of the river remains the same, but its distribution changes depending on the terrain. In this analogy, the river represents the flow of charged particles and energy through interstellar space. The rocks and channels correspond to magnetic fields, plasma structures, and density variations in the medium. Voyager is like an observer floating along the river, noticing that the leaf, or in this case the signal, seems to accelerate or intensify at certain points. The leaf's increased speed is not creating energy out of nothing. It is simply following the contours of the environment that shape its motion. A study published in Nature highlights a similar principle. Plasma waves in interstellar space can resonate with cosmic rays under certain conditions. When resonance occurs, energy is transferred from the medium to the particles, temporarily increasing their observed intensity. This process is analogous to pushing a child on a swing. At just the right moment, the motion is amplified without violating energy conservation. Voyager's plasma wave instruments provided the data to confirm that such resonance can occur in situ, producing the apparent strengthening of the signal. Magnetic fields in the outer heliosphere act as natural guides, much like channels or barriers in the river analogy. Charged particles spiral along field lines, and slight twists or concentrations in the magnetic geometry can focus energy along narrow paths. This focusing effect can make a particle stream or wave appear stronger when observed along the right trajectory. The combination of magnetic guidance, plasma resonance, and the dynamic interface of the heliopause explains why Voyager observes intensity increases in certain regions. It is important to emphasize that this is not a Veil motion of physics. The total energy in the system remains constant. What changes is how that energy is distributed across space. In open interstellar regions, subtle interactions can cause local enhancements that would be imperceptible on smaller scales but become measurable over astronomical distances. Voyager's instruments are sensitive enough to detect these variations, allowing scientists to witness a natural amplification process that would otherwise remain hidden. This analogy also helps to illustrate why the signal's behavior initially appeared so mysterious. In most laboratory or terrestrial environments, we rarely encounter systems where energy is redistributed over such vast scales. In space, even minor fluctuations in particle density or magnetic orientation can produce effects that seem counterintuitive. From our perspective on Earth, energy should decrease as it travels. In interstellar space, however, the landscape is far more complex. Energy can be guided, concentrated, and enhanced in ways that mimic growth without breaking physical laws. Another aspect of the analogy is the effect of turbulence. Just as a river contains eddies and swirls that can temporarily accelerate objects, interstellar turbulence creates small-scale variations in particle motion and wave propagation. Voyager's data suggests that these turbulent effects contribute to the modulation of signal intensity. When combined with resonance and magnetic focusing, turbulence becomes a key element in explaining the signal's apparent amplification. The river analogy also emphasizes the role of observation. Voyager measures the signal from a single point in space, analogous to standing at a fixed location on the riverbank and observing the leaf pass by. The leaf may appear to accelerate or decelerate depending on which channels it traverses. Similarly, the spacecraft observes intensity variations that are dependent on the local structure of the medium. Different trajectories through space would likely produce different patterns of observed intensity, highlighting the importance of spatial context in interpreting the signal. This framework allows scientists to reconcile previously confusing observations. Multi-channel correlations, gradual growth, and apparent amplification are no longer paradoxical. They emerge naturally from the combined effects of magnetic guidance, plasma resonance, and structured interstellar dynamics. Voyager's instruments provided the empirical evidence, while modeling and analogy help to explain why the signal behaves as it does. Importantly, the analogy underscores the need for continued observation and modeling. Just as understanding a river requires multiple perspectives and measurements across different points, understanding interstellar amplification requires data from multiple locations and times. Voyager's single trajectory offers a unique but limited perspective, prompting the design of future missions and observational strategies to test the generality of these mechanisms. In the end, the analogy provides clarity without oversimplifying. The signal is not growing magically or violating physics. Instead, it is being shaped by its environment, moving through a complex, dynamic landscape that guides and redistributes energy. Like a leaf traveling through a winding river, the signal's path is influenced by subtle but significant features, producing the effects that initially seemed impossible. And as we consider this analogy, it becomes clear why the next step in research will focus on mapping these interstellar channels in greater detail to understand not just that amplification occurs, but precisely how and where it happens across the galaxy. Once scientists began to understand the mechanism behind Voyager's signal, their attention turned to the broader implications for the galaxy. If energy can be guided and amplified near the heliopause of our own solar system, similar processes might exist around other stars and planetary systems. The structured interstellar medium with its magnetic flux tubes, plasma waves, and turbulent regions is not unique to our neighborhood. Across the Milky Way, these features could influence the propagation of cosmic rays, electromagnetic signals, and other forms of energy. Observations of other stellar systems suggest that stellar winds and magnetic fields are common. Just as our Sun creates a heliosphere, many stars emit charged particles that interact with the surrounding interstellar medium, forming protective bubbles that define local environments. These heliospheres may vary in size, shape, and dynamics depending on stellar activity, local interstellar density, and magnetic topology. According to models developed by astrophysicists at Harvard and MIT, energy propagating near the edges of these systems could undergo similar focusing and amplification effects as observed in our own heliopause region. The implications extend to the detection of cosmic rays and interstellar particles. Spacecraft studying cosmic rays around other stars may observe variations in intensity that are not solely attributable to source activity, but also to amplification effects caused by structured environments. This realization challenges previous interpretations of data from missions like the Advanced Composition Explorer, which measured cosmic ray fluxes within the inner solar system. Researchers must now consider that interstellar amplification may have subtly influenced observations historically assumed to reflect uniform propagation. Beyond particles, electromagnetic signals from distant astrophysical phenomena might also be affected. Radio waves, X-rays, and gamma rays traveling through regions with complex magnetic and plasma structures could be focused or redirected, altering the intensity and timing of signals that reach Earth-based or space telescopes. In essence, the galaxy itself may act as a subtle lensing environment, concentrating energy in certain directions while dispersing it in others. This could help explain some anomalies in observations of pulsars, supernova remnants, or other energetic sources, where measured intensities occasionally differ from theoretical predictions. The discovery also opens the possibility of new observational techniques. If interstellar structures can amplify energy, then strategically placed spacecraft or arrays of detectors could exploit these natural waveguides to measure distant sources with enhanced sensitivity. This concept suggests that future interstellar exploration might not just involve direct measurement, but the clever use of environmental effects to magnify faint signals, much like using a telescope lens to focus light from a distant star. In addition, understanding these amplification mechanisms has implications for space weather and the protections of planetary systems. Stellar winds interacting with interstellar structures could modulate the intensity of cosmic rays or high-energy particles entering a system, affecting radiation exposure on planets or spacecraft. Voyager's data thus provides insight not only into energy propagation, but also into the broader context of stellar environments and their interaction with the galaxy. Researchers also began to consider how these mechanisms could influence the interpretation of signals potentially originating from intelligent sources. If natural amplification can occur in interstellar space, then signals received from distant civilizations might be distorted, enhanced, or redirected by the structures they traverse. While speculative, this realization underscores the importance of understanding the interstellar medium's influence on energy propagation before drawing conclusions about distant transmissions. Simulations conducted at Caltech and NASA's Jet Propulsion Laboratory suggest that amplification effects vary with the geometry and orientation of magnetic structures relative to the source and observer. In some cases, signals could appear significantly stronger than expected, while in others they might weaken. This variability could account for the intermittent nature of certain observed cosmic phenomena, where measured intensities fluctuate without apparent changes at the source. Voyager's measurements also highlight the scale over which these effects operate. Magnetic flux tubes, plasma channels, and turbulence exist over hundreds or thousands of astronomical units. Energy passing through these regions may experience gradual enhancements modulated by local structures. This scale is vast compared to planetary or even stellar distances, emphasizing that the galaxy is not uniform but a landscape of subtle dynamic features capable of shaping the movement of energy over immense distances. The discovery has encouraged astronomers to revisit archival data from other missions and telescopes. Patterns previously dismissed as anomalies may now be reinterpreted as manifestations of interstellar amplification. For instance, small deviations in cosmic ray intensities recorded by Pioneer or anomalous variations in radio wave propagation might be consistent with the mechanisms observed by Voyager. This reinterpretation could provide a new lens through which to analyze decades of space data. Importantly, this expansion of understanding demonstrates the interconnectedness of astrophysical phenomena. The heliopause, once considered a boundary, is revealed to be a dynamic interface influencing energy propagation. The interstellar medium is not passive but structured and capable of modulating particles and waves. These processes in turn influence observations across the galaxy from stellar systems nearby to sources at thousands of light years. Voyager has provided the first direct evidence, but the implications resonate far beyond our solar system. In essence, the signal that grew stronger beyond our solar system is not merely a curiosity, it serves as a window into the complexity of the galaxy itself. By revealing the ways energy can be guided, focused and amplified, Voyager challenges assumptions about uniformity in interstellar space and suggests that the galaxy is alive with subtle processes that shape the movement of particles and waves over cosmic distances. As scientists continue to study these effects, they begin to see patterns that may apply universally. Stellar boundaries, interstellar structures, and plasma interactions are not unique to our neighborhood. They exist throughout the Milky Way, influencing energy propagation in ways that are only now becoming apparent. Voyager has illuminated one corner of this dynamic environment, providing a glimpse into processes that may be occurring across the galaxy, quietly shaping the behavior of energy in ways humanity has only just begun to comprehend. As the implications of Voyager's observations unfolded, it became clear that our understanding of the heliosphere and interstellar space needed revision. For decades, the heliosphere was thought to act primarily as a shield, a protective bubble created by the solar wind that deflected cosmic rays and separated the Sun's influence from the rest of the galaxy. It was often described as a relatively simple static boundary. Voyager's data, however, revealed a far more dynamic picture. The heliopause is not a rigid wall, but a shifting, responsive interface. Magnetic fields twist and fold, plasma flows fluctuate, and energetic particles interact in complex time-dependent ways. These dynamics can concentrate energy along specific paths, guiding and amplifying particles and waves as they cross the boundary. The realization that the heliosphere could modulate energy in such a manner challenges prior assumptions about its function and the environment beyond it. The edge of our Sun's influence is no longer just a protective zone, It is an active, interactive region shaping how the galaxy connects to the solar system. One consequence of this insight is that cosmic ray flux inside the heliosphere may be influenced not only by solar activity, but also by structural variations at the boundary. Previously, models assumed that shielding effects depended largely on the strength of the solar wind and magnetic fields near the Sun. Voyager suggests that local structures at the heliopause can focus or redirect incoming particles, creating variations in cosmic ray intensity that were not accounted for in earlier predictions. This understanding has implications for space weather modeling and for predicting radiation exposure for spacecraft and potential crewed missions beyond Earth orbit. The amplification of the signal also challenges how scientists interpret measurements of distant astrophysical sources. Signals from other stars, pulsars, or supernovae may pass through regions similar to our heliopause before reaching Earth. If interstellar structures can focus or enhance energy, then observations could overestimate the brightness or intensity of distant sources, leading to revised models of energy output distance or source behavior. Voyager has illuminated a mechanism by which the galaxy itself can shape the signals we detect, emphasizing the need to consider the medium as an active participant rather than a passive conduit. Moreover, the discovery reframed the heliosphere as a gateway rather than a boundary. Energy leaving the solar system does not simply disperse. It interacts with interstellar structures, potentially affecting particles and fields over vast distances. The dynamic amplification processes observed by Voyager suggest that the heliosphere contributes to shaping energy flows into the galaxy, influencing both inbound cosmic rays and outbound solar emissions. The edge of the Sun is thus both a filter and a lens, modulating energy in ways previously unappreciated. This evolving understanding also raises questions about comparative heliophysics. How does our Sun's heliosphere compare to those of other stars? Data from missions studying stellar winds and exoplanetary environments indicate that heliospheric structures vary widely, depending on stellar type rotation rate and local interstellar conditions. If similar amplification effects occur around other stars, it could have significant consequences for the radiation environment in nearby exoplanetary systems, influencing habitability, atmospheric retention, and cosmic ray exposure. Voyager's findings provide a local reference point for interpreting these phenomena elsewhere in the galaxy. The implications extend further into astrophysics and cosmology. Structured energy propagation could influence the detectability of signals across vast distances. In some regions, natural amplification may enhance signals from otherwise faint sources, making them more visible to telescopes. In others, energy could be dispersed or redirected, obscuring observations. These mechanisms may partially explain why certain astronomical objects appear brighter or dimmer than models predict, and why some signals from deep space exhibit unexpected fluctuations. Voyager's measurements also underscore the importance of multidisciplinary collaboration. Understanding these phenomena requires combining heliophysics, plasma physics, astrophysics, and computational modeling. By integrating data from Voyager's instruments with simulations of magnetic field dynamics and plasma behavior, scientists can construct more accurate models of energy propagation at the edges of stellar systems. This collaborative approach provides a framework for interpreting signals not only from our own heliosphere, but from other stars and galactic environments. Perhaps most importantly, this discovery reframes the concept of the edge in space and leads boundaries in the universe are often treated as clear and distinct, whether between planets and interplanetary space, or stars and the interstellar medium. Voyager's data suggests that edges are dynamic, interactive, and permeable. Energy does not simply stop at a boundary, it is reshaped and guided by the structures it encounters. The universe is less a collection of isolated regions and more an interconnected web where boundaries influence flow, focus, and intensity. This insight has profound implications for future exploration and observation. Understanding the dynamic nature of the heliosphere and interstellar medium informs spacecraft design, mission planning, and the interpretation of signals across the galaxy. It emphasizes that space is not merely a backdrop, but an active participant shaping both the signals we detect and the environments through which they travel. In short, Voyager has revealed that the edge of the Sun is not just a boundary. It is a dynamic interface where energy is focused, modulated, and amplified, influencing both the local and galactic environment. By reshaping our understanding of the heliosphere, this discovery challenges long-held assumptions and opens new avenues for exploring how energy moves across the galaxy. The solar system's edge is no longer simply a limit of influence. It is a laboratory for understanding the subtle and complex interactions that shape the behavior of particles and waves across interstellar space. Even with these breakthroughs, much about the signal remains unknown. Voyager has illuminated mechanisms for amplification, but the complexity of interstellar space leaves significant questions unanswered. Scientists are still uncertain about the precise configuration of magnetic fields beyond the heliopause, the variability of plasma structures over time, and the extent to which local turbulence contributes to signal modulation. Each measurement opens new questions, highlighting how little we truly understand about the environment where our solar system meets the galaxy. One of the largest uncertainties involves the source of the initial energy. While Voyager can detect how the signal behaves and measure its characteristics, it cannot pinpoint distant origins with precision. Is the energy primarily composed of cosmic rays, low-frequency plasma waves, or some combination of particle and electromagnetic energy? Could there be a previously unidentified astrophysical source contributing to the intensity? The data provides clues but not definitive answers. Another open question concerns spatial variability. Voyager travels along a single trajectory, capturing a linear sampling of interstellar conditions. We have no lateral measurements to determine whether the amplification effects are uniform across the surrounding region or confined to narrow channels. Are other directions in interstellar space subject to similar intensification, or is this an isolated phenomenon shaped by specific local structures? Without multiple observation points, these questions remain largely speculative. Temporal variability also poses a challenge. The signal fluctuates over time in ways that suggest dynamic processes, yet the precise drivers of these changes are unclear. Solar activity, interstellar turbulence, and large-scale magnetic field reconfigurations all potentially influence the measurements. Separating the contributions of these factors requires sophisticated modeling, and even then uncertainty persists. Scientists are developing simulations to test different scenarios, but the real environment is so complex that models can only approximate reality. Understanding the detailed physics of amplification is another open frontier. Plasma wave interactions, magnetic focusing, and particle acceleration are known to occur, but scaling these processes over thousands of astronomical units introduces unknown factors. For example, how do tiny variations in magnetic field alignment produce consistent amplification across vast distances? How does turbulence modulate energy transfer on interstellar scales? Voyager provides the first in situ measurements, but theoretical work is still catching up. There is also the question of universality. Does this phenomenon occur around other stars, or is it unique to our heliosphere? Observations of other stellar systems suggest that similar structures exist, but no spacecraft has yet passed through another star's boundary to provide direct measurements. Comparative studies of cosmic rays, plasma, and magnetic fields near other stars may offer indirect evidence, but uncertainties remain high. The long-term evolution of these effects is unknown. Voyager is moving outward at about 17 kilometers per second, providing a temporal snapshot along a single path. How might the amplification behavior change over millions of kilometers? Could the signal eventually fade, stabilize, or even intensify further? Without continuous multi-point observations, these questions remain speculative. Another major unknown is how these processes influence the broader galaxy. If interstellar structures can focus or amplify energy, Might they affect how cosmic rays propagate across larger scales? Could they modulate radiation environments around exoplanetary systems, influencing habitability or atmospheric chemistry? These questions reach beyond the immediate measurements and into broader astrophysical implications. Additionally, scientists remain unsure about the relative contribution of different mechanisms. Amplification may result from a combination of heliopause interactions, interstellar medium structuring, plasma resonance, and turbulence. Quantifying the relative importance of each factor is challenging, especially when many variables interact simultaneously in ways that are difficult to observe directly. There is also the philosophical uncertainty of discovery itself. Voyager's signal highlights how direct exploration can reveal phenomena that theoretical predictions alone might not anticipate. It demonstrates that even in a well-studied region of space, surprises await. The incomplete understanding reinforces the need for continued observation, caution in interpretation, and openness to revising models as new data emerges. Ultimately, what we do not know is as important as what we've discovered. Voyager has shown that energy in interstellar space can behave in unexpected ways, yet the full complexity of the mechanisms, their variability across space and time, and their broader consequences remain largely hidden. Each new observation raises further questions, reminding scientists that the universe is far more intricate and dynamic than initial models suggest. This uncertainty motivates new research and future missions, inspiring the development of instruments capable of measuring plasma waves, magnetic fields, and particle fluxes with higher resolution and from multiple locations. The unknowns revealed by Voyager set the agenda for decades of inquiry into the structure and behavior of interstellar space, guiding the next generation of scientists and explorers. Voyager's journey demonstrates that even as we gain understanding, we remain on the threshold of discovery. The signal's persistence and growth reveal phenomena that stretch our models, challenge our expectations, and hint at processes that are only beginning to be understood. And as we confront these unknowns, the pursuit of knowledge itself becomes an adventure, a quest to map and comprehend the dynamic, complex environment that surrounds our solar system. The path forward relies on new missions and next-generation telescopes designed to probe interstellar space in greater detail. Voyager provides a single line of sight, but understanding the full complexity of the heliopause and the surrounding medium requires more data from multiple directions, higher resolution instruments, and longer observation periods. NASA, ESA, and international partners are already planning missions that will extend humanity's reach into these regions, building on Voyager's pioneering work. One such initiative is the Interstellar Mapping and Acceleration Probe, or IMAP, scheduled to launch soon. IMAP is designed to measure energetic particles, magnetic fields, and plasma with greater precision than Voyager, providing a multidimensional view of the heliosphere's interaction with the interstellar medium, by tracking particles as they move across boundaries and through structured regions. IMAP aims to quantify the processes responsible for energy redistribution and apparent amplification. Scientists hope it will validate theories suggested by Voyager data and reveal additional phenomena that have remained undetectable until now. Another approach involves leveraging Earth-based and spaceborne telescopes to observe stellar analogues to our heliosphere. Instruments such as the Hubble Space Telescope, the upcoming James Webb Space Telescope, and radio arrays like the Square Kilometre Array provide the ability to study stellar winds, magnetic interactions, and cosmic ray propagation around other stars. By comparing observations from these systems with Voyager's direct measurements, researchers can determine whether amplification mechanisms are common throughout the galaxy or unique to our local environment. There is also interest in conceptual interstellar probe missions that could carry multiple instruments along different trajectories, sampling energy propagation across various paths simultaneously. Such missions would address the current limitation of Voyager's single trajectory, providing three-dimensional mapping of interstellar plasma structures, magnetic flux tubes, and particle distributions. The goal is to identify whether the amplification effects are widespread or confined to particular channels, and to understand the interplay between the heliosphere and surrounding interstellar structures in unprecedented detail. Technological advances are crucial for these efforts. Miniaturized Bees-Savitboard plasma detectors, high-sensitivity magnetometers and particle analyzers capable of surviving decades in space will enable new missions to replicate and extend Voyager's observations. Additionally, computational modeling continues to advance, allowing scientists to simulate complex interactions in interstellar space with greater accuracy. By integrating observational data and simulations, researchers aim to predict how energy flows and intensifies under various configurations, providing context for future measurements. International collaboration plays a key role in this research. The dynamic nature of the heliosphere and interstellar medium requires expertise from heliophysicists, plasma physicists, astrophysicists, and space mission engineers. Teams at NASA's Jet Propulsion Laboratory, ESA, Caltech MIT, and universities worldwide coordinate observations, share data, and refine models collectively. These collaborative efforts are essential for interpreting subtle phenomena and developing the next generation of interstellar exploration. In addition to probing the heliosphere, scientists are developing new methods to study energy propagation across the broader galaxy. Radio and gamma-ray observatories are capable of detecting variations in particle flux and electromagnetic waves over vast distances, potentially identifying regions where natural amplification occurs. By combining in situ measurements from spacecraft with remote observations, researchers can begin to map how structured interstellar media influence energy on galactic scales. The implications extend beyond astrophysics into practical applications for space exploration. Understanding amplification mechanisms can inform radiation shielding for crewed missions, guide predictions of cosmic ray flux in deep space, and influence trajectory planning for spacecraft traveling through high-energy regions. By anticipating areas where energy may be concentrated, mission designers can mitigate risks and optimize instrument performance. Future missions may also explore the interaction between the heliopause and interstellar turbulence in more detail. Voyager revealed that plasma waves and magnetic fields are highly dynamic, but the fine-scale structure remains unresolved. By deploying arrays of instruments capable of measuring temporal and spatial variations simultaneously, scientists hope to identify the exact processes responsible for energy amplification and quantify their effects. Finally, these missions have broader scientific value. By studying energy amplification and interstellar structures, we gain insight into fundamental processes that govern the galaxy. Understanding how magnetic fields, plasma, and particle flows interact provides context for phenomena ranging from star formation to cosmic ray propagation, and even the behavior of radiation in other stellar systems. The pursuit of this knowledge not only solves the mystery observed by Voyager, but also enriches our overall understanding of the universe. Voyager's legacy is thus both inspirational and foundational. It provides a benchmark for all future missions, a reminder of the insights that can be gained from long-term direct exploration. As new spacecraft venture into the heliosphere and beyond, they will build on Voyager's observations, refining our models and deepening our understanding of the dynamic interface between stars and the galaxy. The journey continues, guided by the signal that first revealed the complexity of space beyond our sun. As Voyager drifts ever farther into interstellar space, it offers more than just scientific data. It provides a philosophical reflection on our place in the universe and the nature of discovery. The signal it observes is subtle, almost imperceptible to the untrained eye, yet it reveals a complexity in space that we had never imagined. It reminds us that even in the apparent silence of the galaxy, processes are unfolding that stretch across unimaginable distances, shaping energy particles and waves in ways we are only beginning to understand. This realization challenges our perception of emptiness. Interstellar space is not a void. It is a dynamic environment alive with magnetic fields, plasma currents, and turbulent structures. Energy does not merely travel passively. It interacts with its environment guided, focused, and occasionally amplified in ways that make the universe feel less static and more responsive. In this sense, space is not just a backdrop to cosmic events, but an active participant in the flow of energy and matter. Voyager's signal also illustrates the value of patience and persistence. Decades of measurement were necessary to identify trends, discern patterns, and distinguish anomalies from noise. The signal did not reveal its full story immediately. Only through long-term observation and meticulous analysis could scientists begin to understand its significance. This is a lesson for exploration. Profound discoveries often emerge gradually, and what initially appears minor can transform into a paradigm-shifting insight. The phenomenon also emphasizes the interconnectedness of cosmic systems. The heliosphere, interstellar medium, and distant astrophysical sources do not exist in isolation. They interact, influence, and shape one another over vast scales. Voyager shows that boundaries are not simple lines or borders, but dynamic interfaces where energy flows are redistributed, transformed, and amplified. In understanding these interactions, we gain a more holistic view of how stars, particles, and space itself interrelate across the galaxy. Furthermore, the growing signal serves as a metaphor for discovery itself. Knowledge travels outward, guided by observation and analysis, shaped by interpretation and understanding. Just as the signal interacts with structures in space to reveal unexpected patterns, human curiosity interacts with data models and exploration to reveal truths that were previously hidden. The universe presents its complexity, patiently rewarding those who follow its subtle signals with insight and wonder. Voyager also highlights the limits of our knowledge. Even with decades of data and sophisticated models, the signal continues to present unanswered questions. The full configuration of magnetic fields, the precise dynamics of plasma structures, and the broader implications for the galaxy remain partly unknown. This uncertainty is not a weakness, but a testament to the depth and richness of the cosmos. It reminds us that the universe is vast and intricate, and that every answer opens the door to new questions. The philosophical reflection extends to the human scale as well. Voyager is a small object, a man-made spacecraft drifting quietly through interstellar space. Its instruments detect phenomena that stretch across hundreds of astronomical units, yet it continues its work with no consciousness, no awareness, simply following the trajectory humanity set decades ago. In this contrast, the signal becomes a bridge between the human and the cosmic. It represents the interaction between our curiosity, our ingenuity, and the vast dynamic universe beyond our immediate perception. This journey also invites humility. Even after centuries of observation, centuries of theory, and decades of spaceflight, the universe still contains surprises. The signal reminds us that space is more intricate than our models, that energy behaves in ways that challenge intuition, and that the cosmos holds processes that operate on scales and in manners beyond our everyday experience. In this sense, exploration is as much about expanding our awareness as it is about collecting data. Finally, the signal encourages a sense of connection. Voyager's observations link the solar system to the galaxy. They show that even at the edge of our star's influence, energy and matter are intertwined with structures and processes far beyond. This interconnectedness fosters a sense of unity with the universe, illustrating that humanity's pursuit of knowledge is a thread in a much larger cosmic tapestry. Every measurement, every observation, every insight connects us more deeply to the mechanisms that shape the galaxy. In the quiet vastness beyond Neptune, where sunlight is faint and the void seems absolute, Voyager continues to listen. It listens to a signal that grows a signal shaped by the interactions of plasma magnetic fields and interstellar structures. And in listening, humanity learns not only about the mechanics of space, but about the beauty and subtlety of a universe that is at once orderly, dynamic, and endlessly surprising. As the signal persists and strengthens, it serves as a reminder that the universe is never truly silent, that boundaries are permeable and interactive, and that even the emptiest regions are alive with subtle processes. Voyager carries this lesson outward, a small emissary illuminating the complexity of space, guiding humanity toward new discoveries and inspiring a profound sense of wonder at the richness of the cosmos.